Mathematica notebooks as pedagogical documents. My name is Roger Williams, and this is a presentation of some concepts for writing Mathematica notebooks as developed by David Park and embedded in his presentations package. This video is about the form and method of communicating technical material, and not specifically about the technical material shown. We will cover some written, graphical, and historical aspects surrounding this central idea. But first, some history. More than 3,000 years ago, a scribe named Ahmose lived in Egypt. He's become famous as the author of the Rhind Papyrus, now housed in the British Museum. He recorded various geometric and engineering problems. Here is one example. The translation of this cuneiform is, if a pyramid is 250 cubits high and the side of its base 360 cubits long, what is its secant? So that's what all this means, I'm told. I can't read it, I admit. A secant is the cotangent of the angle between the base of the pyramid and its face. Here is a rendition using a drawing we can more easily identify. Right down here, I believe this is the cotangent of the angle. I think that's right. Anyway. Now, problem 56 was recorded on a sheet of papyrus, and it is contained in what may be the earliest form of a technical paper we have recorded. There have been some small errors found, either through original error or degradation of the medium. We have an arithmetic example and a diagram for calculating the slope of the side of a pyramid. This sets a technique for technical writing for 3.5 millennium. Also, another problem contains a clear error or copying error or typo, something that plagues static media down to this day. It also clearly has diagrams. Now, hundreds of years later, Euclid was working on his elements, including this proof from the Greek. And this is a great advance. Let's see here. Let's take a look at our drawing. There we go. This is a great advance because we have a formal proof. This is book 1, theorem 11. But again, the presentation is equations and diagrams with some textual discussions, and it's another static presentation. Now we move from here much closer to the current day. This article about enzymatic reactions of lysosomes was almost certainly typed and hand-drawn in the 70s. At first, when you look at the text here, it appears, let's see here, it appears that a ribbon is making some characters stronger than others, but you can also see what appears to be typesetting, where the font width, you see the font width here, is inconsistent. Now this 3D drawing is very nice, I like it. Some of these other drawings are very nice. And it's a potential energy surface, is what this drawing is about. Now a more contemporary example is this physics paper. It's probably just in the last few years. It was probably authored in LaTeX. It has drawings and equations, all related in the mind of the author and the reader, but still static text on the page. Now links in the PDF, such as here, you can see how it's a link, can be included in PDFs, and this has some internal links to references. I think this takes you down to figure 1, which is the figure we were talking about. Now, using an interactive current technology example is this, there are custom applications using Java, which are active and interactive. Here's one about projectile motion. Yeah, projectile motion. I really like how you can change the parameters and rerun the simulation. So I'm going to change this to 50, my angle. And then I'm going to fire it. And you can see where it lands. and then I can go to 65, and I can change the speed to 14, and I can fire it again. Whoa, look at that. I guessed right. It hit the bullseye. I can't believe it. Now, these are expensive, and they don't contain generated knowledge. And a reader can't branch off and continue with other calculations and variations. They are not an easy means of communication, but they do illustrate that people are yearning for something better than a static medium. Let's see. Other modern examples. Here's some more examples. This is a news group, Google Groups news group, sci.math. And this includes a discussion on a math news group. It's all plain text, but it does include links. Here's a link to somewhere in math forum. And it does have some equations down here, which are a little hard to read, but I think we get the picture. And this shows how the modern internet facilitates communication and the generation of new mathematical results. But the medium is somewhat clumsy. And then the result of these discussions back and forth between Dave Cantrell and Rob Johnson, lead to another text document where we have equations and diagrams. So the important point here is that Mathematica is a new and revolutionary development in communications medium, because we want to preserve all that is good about the classic static media, but include the advantages of active and dynamic Mathematica textbooks. Even the term notebook biases us here. It makes us think of lab notebooks or scratch pads or temporary material. We prefer to think of them as advanced technical documents. Now let's preview the nature and advantages of the document that we're going to talk about in the rest of the presentation. So the first thing is that everything in the document is actively calculated. So if I open up a section of it here, these calculations have actually been performed in the document. The starting definitions and rules are clearly shown. They're down here at the bottom. So it's a lot of code, of course. And this means that there's a huge amount of self-proofing going on, and the material has high integrity. If Amos had been using Mathematica to communicate his error, it would surely have been eliminated. The developed materials move down here, where it becomes generated embedded knowledge, which can be actively used in further work or immediately by the reader in trying variations. I'm going to show that here in a minute. The communication is directly usable by the reader. Active dynamic material is easier for humans to understand. Everybody knows that. I think sometimes it's called direct manipulation. We evolved to understand actions much better than static diagrams and equations. The notebook, nonetheless, follows a semi-classical style of presentation that is not just a long string of input-output cells. Indeed, input-output cells are not even part of a classic technical paper, and the major derivation is presented as an organized unity.